Hi guys. Okay, so we are going to cover this chapter on atoms. First, we will look at the elements and the symbols that are associated with those elements. Then the periodic table and the placement of those elements in the periodic table. What are the rows? What are the groups? The names of the groups and the metals and the non-metals and metalloids. So for you guys, it's very important. You should know the names and the symbols of the elements, and you need to start memorizing it. Then you should know how to identify, the metals, non-metals, and you should know, which ones are metals and non-metals and metalloids, and where are they placed in the periodic table. So these are all test questions, okay? Next is the atomic theory, which is just basically the history and the structure of atom, how we came about, how did we learn or how did we know that the structure of atom is. And then we will look at the atomic number and the mass number. So, the historical part you can leave, but at least you should know how to use the mass number and the atomic number to get to the number of neutrons. So, and the protons and the electrons, okay? And the concept of isotopes. What are isotopes? So this is also important. Isotopes, and how is the weight of these isotopes determined, okay? When you put these, how is the average mass of the atom determined, when there are several isotopes, then those things. Then the discovery of the energy levels. Those are just basic things that you need to know. But however, very important is you have an understanding of what the shells are, what the subshells are. Now, the shells are also called a principal energy level, or it's also called a principal quantum number. Okay, so that's the thing. And this is also called a main energy level. And for the subshells, sometimes for the subshells, they use the word sublevels, and it doesn't matter. It just means it's a part of that bigger energy level. So that thing, orbitals and the number of electrons. So those things we will cover. We're going to cover in great detail the electronic configuration of that. All that is going to be on the test. You should know the blocks. You should know what group numbers are. Valence electrons are extremely important because these valence electrons are tied up to the Lewis structures. Okay, so these things. And then the trends in the periodic table is also very important. We're going to look at the size that when you move in the periodic table from left to right, what is the trend? Okay, or the other thing is when you move from top to bottom, what happens? What's the trend? Whether the size increases or decreases, the ionization energy decreases or increases. And this ionization energy actually is also tied to electron affinity. So we will cover that, electron affinity, and this electron affinity is also electronegativity. Okay, electronegativity. So this is all connected. Okay, those things, and then the metallic character. Okay, so before we start with all this, I want you to, first of all, pay attention to, you guys have your work, sorry, I have this other piece opened up, but I'm going to just keep it like that. You guys also have your handouts, okay? So on the handout, it's very important. This was a handout you have, and this is what we will be referring to. We're going to be referring to the group numbers, group periods, and all this, trends in the periodic table and the electronic configuration, everything. And you ideally should be memorizing it, but just in case you can't, you should use that handout for the reference. Anyways, so let's look at the elements and the symbols first of all. What are elements? Now, this is an example of, I don't know which element they've shown here. They haven't listed it, but anyways, elements are made up of only one type of particle. So that is why they are considered to be pure substances, okay? Pure substances from which all other things are built, which means that you can start the chemical reactions. In other words, they take part in the chemical reactions, and they cannot be broken down into simpler substances. Means that they are made up of only one type of particles, and these elements are considered to be like pure substances if they are not mixed with anything, if they are not chemically combined. That's what it means. Okay, so some of their names and the symbols of the elements in the periodic table you will generally find in the books. And, there's no particular order of writing their names and the symbols, but their names are given based on the planets, mythological figures, minerals, colors, geographical locations, famous people. So look at this, uranium. Uranium is uranium, and uranium, like a big name, but the symbol is just U. And the source of the name is the planet. So it's coming, the name is, now why was it named Uranus after Uranus? There is no particular like there might be some story behind it, but why is it not UR? Why is it not UA? That's like, you just have to kind of deal with it with the naming. Okay, now let's look at titanium. Titanium, again, TI, that's the titanium, TI. That is the, the symbol, and the name is coming from Titans. That is their mythology. Similarly, chlorine. Chlorine is Cl. Okay, not the Cl. Now, why titanium has Ti and chlorine has Cl, not Ch? Again, there are no rules regarding that. All these elements, keep this in mind, were discovered at different points of time. Okay, so that's how they got their name. So this is a Greek name coming from chlorus. Iodine is also coming from iodus, which is violet color. And yeah, chlorus is greenish yellow color, so it's after the color. Iodus is violet color. Again, iodine is, the crystals of iodine are violet color. Chlorine as a gas is greenish yellow gas. So that's why they gave those names after the Greek names. And iodine, why chlorine is Cl and why iodine is not IO? There's no rule. So that is why, just like human beings have names, right? Human beings have names. Similarly, you guys also need to just keep this in mind, that these elements have names, and memorization is the only way. You can characterize them a little bit like I'm showing you how. Next is magnesium. Magnesium is Mg. Okay, and not MA or MN or MS or anything, but it's coming from, it's a magnesia, it's just a mineral. Okay, next is californium. It's named after a place, California, of course, and CF. So you see, the letter is 1, 2, 3, 4, the fourth letter. Okay, now cuprum is curium. Curium is named after the person Marie Curie, and Copernicium is named after Nicholas Copernicus. Okay, so there are, when you look in the periodic table, you look at the symbols and the names of these elements, you will recognize them as, whether it's name of a person or a place, or some mythological figures, you will know them anyways. But some of the names are very simple names, and they're easily, you can remember them. The one letter symbols, for example, are in, sorry, this is all messed up here, but one letter symbols like carbon, like nitrogen, like fluorine and oxygen. So these are one letter symbols. So these, and sulfur and phosphorus also. Okay, and hydrogen also. Okay, so those are the ones. So these are just some examples they have given in this here. But two letter symbols like cobalt is CO, calcium is Ca, aluminum is Al, and then magnesium, Mg. So some of them, you kind of start getting a feel for it. So you will have to create your own notes. And my recommendation is you write a name and write a symbol. And this way, when you write it, then you kind of get a feel for it, eye-hand coordination, those things. So that's one way. Okay. Now, some of these are the common ones they have given you in this table and in your books also, some common names and the symbols. Now, these are very common ones, okay? So again, there is no hard and fast rule, but let's just go by this naming. Aluminum is Al, argon is Ar, arsenic is As, Ba is barium, B is boron, Br is bromine, cadmium is CD, calcium is Ca, carbon is C, chlorine is Cl, chromium is Cr, cobalt is Co, copper is Cu. It's after the Latin name cuprum, okay? And fluorine is F, okay? Then comes the other ones like gallium is Ga, gold, aurum, a Greek name, or I think it's Latin name, Au. Okay, helium is He, hydrogen is hydrogen, iodine is I, iron is Fe, lead is Pb, lithium is Li, magnesium is Mg, manganese is Mn, mercury is Hg, neon is Ne, nickel is Ni, and nitrogen is N. Next comes here, oxygen is O, phosphorus is P, platinum is Pt, potassium is K, radium is Ra, silicon is Si, silver is Ag, sodium is Na, then strontium is Sr, sulfur is S, tin is Sn, and titanium is Ti, uranium is U, and zinc is Cn. So you should make a note of this with your own handwriting. So this way, don't type, handwrite. So then you remember this way. Okay, so these are the common ones. Anyways, let's look at this now. Chemical symbols like silver and gold, they are coming after the Latin name. Silver is Hg. So you see, some of the names are not matching with the symbols. So those names are the Latin names. Silver is argentum, as gold is aurum. Okay, but now that's why these are elements, because if you take gold, you break it up into the tiniest particle that still retains the physical and the chemical properties of gold. That is, it is shiny, it is yellowish color, and it is hard, it's metallic, all those characteristics. The tiniest particle that still retains the physical and the chemical properties, that smallest particle is the atom. Okay, so that means gold is only made up of only one type of particles, and those are, that's why gold is an element. Similarly with silver here, silver, no other particle is there, only one type of particle. And that type of particle is several particles, but all of them are the same. So that is silver. Okay, now comes write the correct symbols and names for each of the following elements. So iodine, iron, let's do this. Iodine, iron, magnesium. This is the, let's do this one here. Okay, let's do study check of iodine, iron, magnesium, zinc, and nitrogen. Let's do this here. Okay, so here comes this question. First of all, the names and symbols. Okay, so the question is, write the names and the symbols of iodine, iron, and which was that? I forgot. Where was that? Iodine, iron, magnesium, zinc, nitrogen. Magnesium, zinc, and nitrogen. So actually, I swapped it. So these are the symbols. These are the symbols here, and the names. So they gave you the names and they ask you to write the symbols. So that's the so this is iodine, okay. Then comes iron. Then comes magnesium. So zinc. Okay, and then nitrogen. So see how I have written this. So this is how, if you do this, you can get a practice of these, okay? All right, next look at the study check problem. Here is the study check, and that is 4.1. Okay, so here they are saying, write the chemical symbols for the element silicon, and for sulfur, SULFUR, and the rust is silver, SILVER. So the question here is that silicon, again, you have to memorize it. Silicon is Si, sulfur is just S, and silver is not something with S, but it starts with AG, okay? So that's one piece where you need to, the more practice you do, the more, the more, better it is going to get. Next is, we are going to look at the periodic table. Okay. Now, let's see if there's anything else I left here. Give the names of the elements in the following symbols. Let's do this also. Names of the elements with the following symbol: phosphorus, aluminum, manganese, hydrogen, potassium. Phosphorus, aluminum, manganese, hydrogen. Phosphorus, aluminum, manganese, hydrogen, potassium. HK. Okay, so the question here, give the names of the elements with the following symbol. Okay, give the names of these elements with the following symbols. So here, these symbols are given, and again, what are their names? So the names, if you write it, you will get it. So here is the name. This one is phosphorus. This one is aluminum, ALUMINUM. This is MN is manganese, GANESE. Hydrogen, HDR, hydrogen. And K stands for potassium. Kalium, it's actually the name, Latin name, kalium. Okay. All right. Next is, so this was actually the worked example, but the rest is all, Okay, next we are looking at, so I walked you through the, these slides in the periodic table. I mean, the slides in the deck, from the chapter slides. Okay, so here we are going to look at, these are the slides, because here's the thing, I don't like to use the slides that are made by the, these publishers of the book, because they are incomplete, and I don't see the connectivity is not there much. But anyways, they're good, for visually looking at the data or, the concept. So that's what it is. So here's the periodic table. We will walk you through the periodic table, the groups, periods, all those things. So this is much better explained through this piece right here. So this is your periodic table. Okay. All right, now this is on the internet from the, you just type in periodic table. It's a dynamic periodic table. Okay, so you have an idea of what the elements are. And actually the elements, I can show you a little bit more of the elements. Just give me 1 second here. Okay, so let's look at this, how the elements, they kind of look like, okay. So let's say, for example, you've seen copper wires, right? So copper wires are made up of only one type of particles. Those are called the atoms, the smallest particles, and they all retain the physical and the chemical properties, the smallest particles. So what is the physical, the chemical properties, and what is the, the weight of so the density and the weight. So if you look at the atomic weight is 63, all the particles will have the weight of the atom, and that weight of the atom is 63 atomic mass units. Okay, overall the density of copper is 8.96 grams per centimeter cube, which means that it is going to sink in water. Look at the melting point, it's very high, 1084 like degrees Celsius, that's roughly. Boiling point is 2500, in that range, degrees Celsius. So pretty high boiling, so it's not, that means that it's not going to melt easily. Okay, so we all know that copper is used in making, these copper, coins and copper rings, and copper, it has another property. You take copper, and if you move the electrons in the copper, and we will study this in a minute, what are electrons and what is that? But anyways, when copper combines with another substances, That means the electrons are shared or the electrons are transferred. And whenever the electrons are transferred, charges are formed. So copper forms a charged species called the ions, but they are blue colored. So you're going to study this further, but this is just a basic introduction, for you, so you understand what the elements are. Okay. Next is, let's say, for example, the elements like, let's say, neon. Now, neon, again, neon, if you pass electrical current through the neon gas, it gives you a bright red glow. So this is used in the advertising signs, right? So its atomic weight, that means the weight of the smallest particle of which neon is made up of, the weight is 20 atomic mass units, okay? The density is 0.9 grams per liter. Now that means that it's like really like, it's very less, like it's a very light gas. Okay. Now negative melting point and boiling point always means that it's a gas. Okay. So neon is used, in the neon signs, and you've seen that. So that is an element. Okay. Now comes argon. Same story with argon. You pass electrical current to it, it becomes, it gives you a blue color. It's a very characteristic color, okay, of this gas, argon. The atomic weight, the weight of the smallest particle of which argon is made up of, that smallest particle, means argon is not made up of anything else, only one type of particles. And the smallest particle, the weight is 39, okay? And now let's look at, for example, let's look at mercury. Where is mercury? Mercury right here. Okay, mercury, we've already seen that mercury, if it's just by itself, that is the one that is found in the thermometers, right? It flows. The moment if somebody has a high temperature, the moment you put mercury, then it just, it shoots up and it tells you what is the degree of hotness, okay? So that's mercury, made up of only one type of particles. The weight of the particle, those particles is just one particle. The weight of that one particle or the atom is 200.95 atomic mass units. Okay, density is 13.53. It's pretty dense, means it's going to sink in water. Okay, now everything is comparative. Okay, so this is the deal with mercury. Now the same mercury, which is, if it's in just an elemental state, means that it is only made up of one type of particles. It's pure, some pure mercury. Then that mercury is very toxic. Okay, it causes neurotoxicity. But the same mercury, if you mix that mercury with, I believe it's zinc or magnesium, then it can be you can put this in the tooth, dental amalgam. You can put it in the mercury, you can put it in your mouth, and I can't see what else it's made up of, but it is, anyways, I believe it is zinc. Then it's safe to put it in the mouth. Then its neurotoxicity, excuse me, is demolished. It doesn't, it's not neurotoxic anymore. And so that leads us to another question of chemical reactivity. How do the substances behave? Now let's look at a few more. Let's look at, for example, hydrogen. Hydrogen is a gas, right? And it is the smallest, atom in the periodic table. It is the element with the smallest atoms, the size of the atoms is really very small. And so, but interestingly, these are responsible for the birth of the stars. This is a very famous, NASA picture. Anyways, let's look at now sulfur. Now, sulfur, you must have seen, sulfur, sometimes this is in the, like mud baths, they put it to give like skin, like if someone suffers from eczema or psoriasis or some kind of skin problems, then, sometimes they go to these sulfur springs, or they take these mud baths, which are laden with sulfur, and so this is has a huge medicinal property. So anyway, sulfur looks like this. Solid white color. Sulfur is also responsible for the tears, in your eyes when you are cutting onions. And even that smell of garlic is because of sulfur. That's the only thing with sulfur compounds. Sulfur compounds are they smell bad. That's the only thing with them. Okay, but anyway, so that's sulfur. Let's look at a few more. Let's look at sodium. Now, sodium is very soft, very, very soft. So if you need to, cut sodium, I mean, if you need to work with sodium and you need certain amount of sodium, then you need a knife to cut this, because it's like a butter, but it is very reactive. So they put it under the oil. Okay, so the same sodium that you eat in your salt, right? That same sodium, if it is just by itself, because a salt is a chemically combined, it's chemically combined with chlorine. But if sodium is just by itself, then that sodium is, is very reactive. It can catch fire. So what we do, we put it under the oil, okay, and then we take it, we handle it very gently, okay. So anyway, so you get an idea. Explore this more, and you can actually see the various what is it called, the applications of these elements. Like, for example, iodine, right? Iodine, violet color, right? And it fumes, it's always subliming, in other words, from solid to gaseous state. So gaseous state is also very purple colored vapors. It's beautiful, okay, but it's toxic. But anyways, so iodine is also used for, like, medicinal purposes. Like, this is a tincture of iodine used for swabs, so that's the thing with iodine. So I highly recommend that when you go down these, you will see the different applications of these elements. Now, in the pure substance, yes, they are used for whatever, several reasons. But once they get chemically combined, then a whole new ball game occurs. Then of course they are not pure. I mean, they may still be considered pure, but they are not made up of atoms. Then when they chemically combine, then they are made up of molecules. So compounds made up of molecules, elements made up of atoms. Okay, so we covered that in chapter 3 already. All right, now let's look at the periodic table and the arrangement of these elements. So what we see here is that these elements are arranged in a certain pattern, and the pattern right here is this guy. Over here you see 2 numbers of hydrogen, right? If you look at these numbers here, the top number is called the atomic number. This number is the atomic number, and this number at the bottom is the mass number. Okay, so before we go further, it's best that we look at the electrons, the structure of atom. Okay, what is that structure of atom? We will cover this, we will cover the history a little bit later, because it's just so the knowledge, so structure of atom. So, okay, so they said through several researches, discoveries, and a lot of, mathematics was also involved to prove all this, that the smallest particle, this is the smallest particle of an element, smallest particle of an element. And this element can be anything. It can be whatever you see. There are 118 of them in the periodic table. Okay, so now the center part is called the nucleus. So this was all discovered through the experiments also. So this is the nucleus, and this nucleus is made up of protons. It is made up of protons, and it is also made up of neutrons. So neutrons and protons are together found in the nucleus. Okay, and another thing is that the nucleus is positively charged. As many number of protons are there, as many plus charges are there on the nucleus. Okay, so the charge on the nucleus depends on number of protons. Okay, and now let's just do this. Protons, let's put it P plus, and neutrons is N0. Why? Because protons, the size is, the charge is positive, okay? And neutrons, the charge is neutral, Okay, zero charge, no charge. Okay, next is all around the nucleus is an empty space, and in that empty space we have these energy levels. So just like solar system, there is a sun in the center, and in these orbits we see the planets are revolving and rotating. So the same thing with the electrons that are found outside these electrons are found outside in the energy level. So these electrons are, so these are the energy, sorry, let me use a different color, energy. This is the energy level. Okay, in the energy level, the electrons are found. This is also energy level. This is also the energy level. So different energy levels, and this is where we see the electrons. Okay, now these electrons are, what are they doing? They are spinning. The electrons are rotating, and they are revolving, or revolving rather, they are spinning on their axis. So when they are spinning on the rotating and spinning, means they are able to, they also exist as wave, and they also exist as particles. Okay, and the electrons have a negative charge. Electrons are negatively charged. Okay, now protons, the size, the actual weight of the protons is 1.0. Protons is 1.007 atomic mass units. Okay, this neutrons has 1.008 atomic mass units, so a little bit higher. And the electrons are very small. It's 0.00055 atomic mass units. Okay, so that's the their size. But at the same time, you can also look at it that if this is also equal to 1 by 1/836 the size of protons. So really tiny, right? Practically, negligible size. Yet the main bulk of the atom is the atomic, in the center, in the nucleus. So we have here the mass number, the mass is the atomic number. The mass is the mass of an atom, that is called the mass number. And the mass number is also represented as Z. Okay, but what is it? Because it's made up of the nucleus is the main thing. So here we have the number of protons plus the number of neutrons. So this is what gives you the mass number, the mass. Okay, then we have the atomic number. Now atomic number is equal to the number of protons. Okay, and the number of protons should be equal to the number of electrons for neutral atoms. Neutral atoms means that when the atoms have no charge. Okay, no charge. All right, now let's look at some examples here before then we delve into the periodic table. Okay, let's say, for example, let's look at an example of nitrogen. Okay, nitrogen, for example, nitrogen. So you will see two numbers on nitrogen. Now, this can be written as, this number can be written as like this. This can be written as this. This can be written as this. This can be written as this. Either way, it doesn't matter. Sometimes you will also see like that. And like that depends, what are we focusing on, atomic number or mass number. But all these are correct. Okay, just a matter of like typing. But let's look at this. So the questions that can be asked, what is the mass number of nitrogen? The mass number of nitrogen is the bigger number. Okay, the bigger number, and that bigger number is 14 and the smaller number is 7. So the mass number is 14. Atomic number is 7. So the next question is, how many number of protons? Number of protons is equal to the atomic number. So that is equal to 7. Next question is, what is the number of electrons? And that number of electrons is is also 7. Okay. Next is, how many number of neutrons are there? The number of neutrons is the the mass number minus the atomic number. That can also be done. Or you can just say the mass number minus the number of protons. Okay, so we have here the number of neutrons. Mass number is 14 minus the atomic number is 7. So the number of neutrons come out to be 7. Okay, so here is the main thing. So number of, let's write this down here. This is the protons, this is the electrons, and that is the neutrons. Okay, let's look at one more example, and then we'll put this whole thing in the periodic table. All right, let's say, for example, okay, how many neutrons are in the nucleus of bromine that has a mass number? So let's do the study check. Study check. (4.4). And here the question is, how many neutrons are in bromine atom that has a mass number of bromine atom is equal to 80. Okay, so how many neutrons are there? So what will you do? You are going to write down the things that you already know about bromine. So consult the periodic table. Consult the periodic table, because you don't have to memorize the mass numbers and the atomic numbers. You should just look at the periodic table for bromine and write down what is the bromine. You will see two numbers. One is the 79.90, and then 79.90 is 80. Okay, and the other is 35. So 35 and 80. This means that the atomic number is equal to 35, and then the mass number is equal to 80. Okay, now the question is, how many neutrons? So the number of protons for bromine is 35. Protons is equal to 35, and the number of electrons is equal to 35. Okay, then the mass number is 80. That means then the number of neutrons is equal to mass number minus the number of protons. Okay, number of protons, and that is here we have number of protons, and that is the 80 minus 35, and that comes out to be that is 45. Okay, 45 is the number of neutrons. Okay, so these type of questions can be asked on the test. So, we may give you uranium, we may give you lead. Okay, another way of testing you is like, whether do you know the names and the symbols? So we may write down, give the number, like for example, potassium, Potassium. So you should know what is potassium. So periodic tables sometimes don't give you the actual names, they just give you the symbols. So you should recognize that potassium stands for K. okay, and not P or anything else. So anyway, so that was your test question. So now it becomes easier for me to actually walk you through the periodic table, and then we will just cover the history later on. But now let's look at the periodic table. Okay, now hydrogen, as you see, so the top number is the atomic number. The bottom number is the mass number. Now, mass number, why is it made up of? If there are exact number of protons and neutrons in the mass, in the nucleus, why do we have the decimal? Where is that coming from? So that is coming from the, this is the average weight of all the isotopes. And we will cover that next. But let us just look at now that pretty much all of the elements have some, isotopes. So their atomic weights or the mass numbers are in decimal points, because we have included the abundance factor, then calculated the average weight of the isotopes. Okay, so we will discuss that more, but let's look at the periodic table now. Periodic table is arranged in the increasing order. Now your book says that in increasing order of the mass number. Yeah, of course the mass is going to increase, but it is more important that you understand that it is the atomic number. So why? Atomic number represents the number of protons. Simple. So if there is only one proton, it is always going to be hydrogen, nothing else. So the identity of the atom is tied to the number of protons. Okay. So if there's only one proton in the atom, hydrogen, you add one more proton to it, make it two protons. Okay, two protons. And what does it become? It becomes helium. Okay, 2 stands for the atomic number, and that atomic number is the number of protons. And now what do you see here? You see that the two protons, hydrogen was highly reactive, but helium is non-reactive. So that changes the chemical properties also. Physically, yeah, both of them are gases, but chemically, helium is inert. It does not react with anything. Okay. Now, helium is a gas. You can't see it. You've seen the gas balloons, but you haven't seen the gas, right? So that's helium. If two protons are there, helium, that's fine. But you have one more proton and it becomes lithium. And lithium is a solid. It's a metal. And it is so reactive that it is placed under the oil. Okay, so this lithium has 3 protons. So that identity, if anytime there are 3 protons in the nucleus, it's always going to be lithium and nothing else. Okay, now the same lithium, which is like soft metal and it is reactive and it's placed under the oil, if you add one more proton to the nucleus of the atom, it becomes beryllium. It's a totally new substance, beryllium. Okay, it's a totally new, it's called the alkaline earth metal. Okay, next, 4 protons give the characteristics of beryllium. 5 protons make a very shiny metal, which is boron. Now, if you add one more proton to the nucleus, that is 6 protons. So the same shiny substance that was before now becomes dark colored, black colored, like a charcoal or a powder or a rock, like that. And that is carbon. So six protons, you could see a black substance sitting on the table, right? But if you have one more proton added to the nucleus, that black substance vanishes. It becomes nitrogen. Okay, one more proton, it becomes oxygen, and the atom, then one more proton, when is added to the atom, it becomes oxygen, and this oxygen is a life force. But one more proton, when it's added, it becomes extremely toxic, and that's fluorine. So you see, the identity of the substance, the identity of the atom changes with the number of protons. And that one more proton, when it's added, fluorine that was highly toxic now becomes non-toxic. 10 protons, that's neon, and it's a gas. The 10 protons made an entirely new substance, which is neon, and it is gaseous state. If you add one more proton to it, you couldn't see neon, but now you are able to see sodium. And again, it's a soft metal. It is very reactive. It is placed under the oil. So if you need to take out sodium, you just need tweezers and pull it out, a small piece. So that is sodium, okay? So that's 11 protons. And then, yes, highly reactive, soft metal kept under the oil, that all these are the properties of sodium. But if you add one more proton to it, it becomes magnesium. It's like metallic, it's like a strip, it's grayish colored, not very shiny, but you have to rub it to make it shiny, but it is reactive, yes, but that is solid, and you don't have to put it under the oil. So that's magnesium. You can cut it and you can weigh it, but sodium is like soft, that's why you're using the tweezers to cut it. Okay, so that's magnesium and so forth. So you get an idea, right? So as you increase the number of protons, the identity of the atom changes. So that's one piece. Second thing is these elements are arranged also in the increasing order of their chemical reactivity. So as you place these elements in the periodic table, as you place them, they all behave, the elements that behave the same way chemically are placed in one column. So if you take lithium, sodium, potassium, and you add water to them, their behavior is going to be the same. So all three of them are going to make shh, like that kind of a sound when they are in the water, and they're going to release hydrogen gas. So all the three, lithium, sodium, potassium, these three guys, their chemical behavior is the same. The only thing that is increasing is the intensity of behavior. So lithium goes like a little bit shh, but sodium goes with more intensity and a few sparks, shh, like that. And potassium, the moment you add it into water, boom, that's an explosion. Purple colored flames are produced. So that's the characteristic, but their behaviors are the same. They're all three of them are behaving with the same way, but they're also producing the same type of gas, hydrogen. So you see that these elements are arranged, all of them, in a certain specific, that order is based on their chemical reactivity. So that's one thing. Next is now a broad categories. Next is, you see that these numbers on the top, and then these numbers on the side, the numbers on the side, 1, 2, 3, 4, and the numbers on the top. The numbers that are on the top, these are called columns or groups. They are called groups. And yeah, just for the sake of, they made it as 1, 2, 3, 4, 5, 6, 7, 18 electrons, 18 columns. But in reality, they are actually better to place them as 1A and 2A, because they are representative elements, means that they are found more in nature. So 1A and 2A, and then you come here, you have this 13, 14, 15, 16, 17 are actually 3A, 4A, 5A, 6A, 7A, and 8A. Okay, so 13 is actually 3A, 14 is actually 4A, 15 is actually 5A, 16 is actually 6A, 17 is actually 7A, and then comes 18, 8A. Okay, next is these guys here in the middle. These are the ones in the middle are the red ones. These are not representative elements. So these are called the transition elements, and then the post-transition, but these are the transition elements. Okay, now let's look at the metals. Now let's look at metals. Now, okay, let's look at these. Oh no, something is, no. Okay, it's not letting me do this. But anyways, you see this gray colored, the alkali, Give me 1 minute. Okay, let's look at this now. So group 1A and 2A. Group 1A, alkali metals. So it's right now, it's not letting me, just focus on just one column, but that's fine. So at least it's colored. So look at the brown colored. The brown colored, they are all grouped in one column, and that group is called alkali metals. The group of elements that are present in group 1A, alkali metals. The group of elements that are present in group 2A, and group 2A is beryllium, magnesium, calcium, strontium, barium, radium. Okay, the light brown ones, and that is the alkaline earth metals. These are called alkaline earth metals. Then these guys don't have any specific, these boron. No, this is again not letting me do. Okay. Anyway, so boron, carbon, nitrogen. There's no specific name to these guys, but however, fluorine, chlorine, bromine, iodine. Okay, so these are called halogens. Okay, fluorine, chlorine, bromine, and iodine. These are halogens. And these guys over here, helium, neon, argon, krypton, xenon, and radon, these are called noble gases. Okay, so group 8A, 18 here, but it's actually 8A is noble gases. 17 is 7A, and these are called halogens. Okay, now let's look at these guys are in the middle, the gray, the red ones, or crimson color. These are called transition metals. Okay, transition metals, and the transition metals are, commonly you see copper, iron, silver, right? Chromium, these are commonly, you've seen them, zinc, silver, gold, mercury, all these are tungsten, that's found in the bulbs. So these are transition elements. But look at the blue ones, these guys over here, the blue ones, these are called post-transition elements. So they behave, more like metals, these guys over here, the blue ones. Okay, now non-metals are carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, selenium, and iodine. These are non-metals. These non-metals are very reactive. Okay, they react with pretty much all the metals. And now pay attention, in between the metals and the non-metals are these guys. These are on a step ladder. The dark green ones, that is boron. It's a metalloid, means it has the characteristics of the metals and it has the characteristics of the non-metals. Now, what are the characteristics of the metals and non-metals? We will see this. But if you look at silicon, germanium, arsenic, antimony, tellurium, and astatine, these are present on a step ladder, and in that step ladder they are called metalloids because they have some characteristics of the metal and some characteristics of the non-metals. Okay, so we will look into what are those characteristics, but that is one big piece right here. Next thing is columns. These columns, they also represent the charge. Charge is when the electrons are lost, a positive charge is formed, plus charge. Okay, so group 1A, all the elements that are in group 1A, they contain one electron in the last shell. All these elements, all this hydrogen, lithium, sodium, potassium, rubidium, and cesium. Okay, so these guys, they have one electron in the last shell. Okay, so we talked about those shells, right? One electron that is present in the last shell. That is why all of them are placed in group 1A. That means they will form only one bond, which means that they will have +1 charge. Okay, next is, look at beryllium, magnesium, calcium, strontium, barium, radium. Okay, these guys are present in group 2A, one electron in the last shell. Oh, sorry, 2 electrons in the last shell. I take that back. 2 electrons in the last shell. That is why they are placed in group 2A, and they will form +2 charge and they will make 2 bonds. Next is, look at these guys over here, boron. This is just not letting me, it'll just, okay. Anyway, so boron, aluminum, gallium, indium, thallium. Okay, so boron, aluminum, gallium, indium, thallium. 13. that is 3a. So all of them will have 3 electrons in the last shell. They will make 3 bonds and they will have mostly +3 charges. Okay. Next comes carbon, group 4a, silicon, germanium, tin, and lead. So these are present in 14, which means 4a. That means that these guys will have 4 electrons in the last shell. They will make +4 charge or -4 charge, or they can form charges by bonds by sharing. So they'll make 4 bonds basically. Okay, so 4 electrons in the last shell, 4 bonds. Now pay attention to this: nitrogen, phosphorus, and then we have arsenic, antimony, bismuth. So not nitrogen. Nitrogen is belonging to 15, which means 5a. This also means that nitrogen has 5 valence electrons in the last shell. Now pay attention, 5 valence electrons in the last shell, and it only needs 3 more to get an octet. We will study this octet more, but just so you know, you get introduced to it, that nitrogen will only make 3 bonds, because 5 plus 3 is equal to 8. So nitrogen will make only 3 bonds. Okay, and it will have 5 valence electrons, but it only needs to make 3 bonds. Okay, so it will generally they share. Same is the case with phosphorus and similarly others. Then comes oxygen. Now oxygen belongs to group 16a, means that 6a. This means that oxygen will only make 2 bonds. So 6 valence electrons, but only will make 2 bonds, means it will have 2 negative charges. Nitrogen 3 negative, oxygen 2 negative, sulfur 2 negative. Okay, so they are all making 2 negative charges. So the driving force somewhere is 8 electrons. So losing electrons, gaining electrons, and we will cover that more, but just so you get used to listening to the things that are going to be coming ahead. Okay, so here is your fluorine, bromine, iodine. They are present in group 17, means that they are present in group 7a. That means they have 7 valence electrons in the last shell, and they will make only 1 bond. Group 8a, helium, neon, argon, krypton, xenon, 8 valence electrons in the last shell. They won't make any bond because their octet is met. So octet means wanting to have 8 electrons in the last shell. Okay, and that can be accomplished by either giving away the electrons or accepting the electrons. So we will cover this more, but look at this number on the side. This means hydrogen is kept in period 1. That means it has only 1 energy level. Where that their electrons are found outside the nucleus, so only 1 energy level. Lithium has 2 energy levels. Sodium has 3 energy levels. Potassium has 4 energy levels. Rubidium has 5 energy levels. 6 and 7. Similarly, they are will have 6 energy level and 7 energy levels. Now that's one piece. Next is the trends we will cover later, but let's look at transition elements, the middle ones. The middle ones are the transition elements. Now here's the thing important. If you look at group 4a, so this is the fourth period. Fourth period, it stops at calcium, but scandium starts with 3D. So it's 1 number less. So scandium starts with 3D. Ytterbium starts with 4D instead of 5. Okay, keep that in mind, that it's one number less. But all of them, they're by default, all of them will have like +2 charges. In other words, 2 electrons in the last shell. And then many other things can also happen. Okay, so this is a very basic introduction of the periodic table. And now let's look at the some of the things that we covered and just walking you through the slide. So here also, again, showing you that the periodic table, how it is placed, 3 broad categories: metals, non-metals, and the metalloid. So you should know in the periodic table what element is present where. Now let's look at the group numbers. Now group numbers are we already talked about, the numbers that are written on the top. So here we have group 2A. So these elements are here, and then you have the rows. So if next thing is the kind of questions that can be asked on the exam is find the element that is present in, let's do this. Okay. Okay, so here we have, just do this. Okay, so the periodic table. So placement is one thing. So what is, do you recognize that the element is placed in a certain period, in a certain column, and can you recognize where is that? So placement of elements. Okay, so now let's look at the placement. For example, the element, find the element, or locate the elements, rather, not find, or locate the element that is present in group 2A and period 4. Okay, so how would you do that? You are going to look at the, let's see here, group 2A. So 2A stands for the second group. That means a column. So we are looking at this column, 2A. So it is present in the fourth row, right? So here is your first row. This is your second row. This is your third row, sorry. And next is your fourth row, number 4. Now this number 4, okay. Next is, so it is present in 2A, calcium is present in group 2A, where it says 2, that is group 2A, and in the fourth row is calcium. Okay, so looking at the periodic table, and that is calcium. Okay, now let's see if we have anything from the book, some examples. Okay, and then identifying them as identifying these elements as metals, non-metals, and metalloids. So let's look at study check. Here is 4.2. Study check. Okay, strontium is an element that gives the brilliant colors in the fireworks, that is the red color. Okay, so that's the strontium. In what group is strontium found? So that's the first question. Identify the group number of strontium. So you need to know the same thing here. This is like, testing your knowledge of the symbols and the names of the elements. So that's important. So we talked about strontium. So what group number it is in? So you go back, look at the periodic table, and if you remember strontium is Sr, or you should know where to look at. So this is present in group 2A. So just write this down, is present in group 2A. Okay, next is the what is the name of this chemical family? So chemical family, or what is the name, or what is it like? In other words, what they're saying is that the groups, the name of the group, what is the name of this group? So you should know, by this time, or you should make a note of it in the periodic table, that group 1A were all of them were alkali metals. Group 2A, all of them were the alkaline earth metals. Okay, the middle ones were the transition elements. Then these guys from boron, carbon, nitrogen, oxygen, there's no group number name, but fluorine, chlorine, bromine, iodine, these are called halogens. And helium, neon, argon, krypton, xenon, radon, these are called the noble gases. Okay, so that's the names of the group. So anyway, so we are looking at strontium, and strontium belongs to alkaline earth metal. This one is the alkaline earth metal. So let's go back and write this down. The chemical family is alkaline earth metal, okay, or element. Okay, next is in what period is strontium found? So they are asking what row or what period strontium is found. So you go back, look at the periodic table. Strontium is found in the 5th period. Okay, strontium is found in the 5th period. 5th period. And then comes the last question, that is strontium a metal, non-metal, or a metalloid? Whether it's a metal, whether it's a non-metal, or is it a metalloid? Okay, so we know that strontium belongs to the metals, and it's not a non-metal, it's not the metalloid. Okay, so this was your study check problem from the book. And now we're going to just quickly run through the history and just see, how did the atomic structure come into play. And then we will just look at next concept. After that is the isotopes. So next is, so we covered the periods, rows, and groups. We covered the names of the groups. We covered the metals, non-metals, and the metalloids. And we covered the symbols. Okay. Next is, this is just going to be a quick thing. We covered the atomic number and the mass number. Okay. Next, let's look at now the historical part of the Dalton's atomic theory. Okay. Next is the structure of atom. Okay, so as you can see, this on the screen, they have shown you the aluminum foil. So aluminum foil is made up of only one type of particles, and these particles that still look like the aluminum foil shine, making that crinkly sound, then very high boiling point, very high melting point, solid, but it can be made into a thin sheet. That is why it's coming as an aluminum, and then also made it into, wires. You can make aluminum wires also. Okay, so that's the metals, the characteristics of the metals. Okay, so an atom is the smallest particle of an element that retains the characteristics of that element. Okay, so John Dalton is credited for coming up with the atomic theory. So he said that atoms are the tiny particles of matter of an element, are similar to each other and different from those of the other elements. So they are very characteristic. Okay, so elements that, each element will have a very unique atom. Okay, no two or more different elements combine to form a compound. So if the elements are going to react, then in the reaction, they will produce a new substance. And the name of the new substance is called compound. And then whatever that new substance is depends on, what the elements were combined and the capacity. So you see, when I was walking you through the periodic table, I was talking about the charges, and I was talking about how many bonds it can form. So that formation of bond occurs through a chemical reaction. Okay, and anytime a chemical reaction is happening, there is always a rearrangement, occurring. It's in a very, very defined order. Okay, atoms can never be created, can never be destroyed, but they are transformed from one form to another. And that is the premise of the chemical reaction, or it is a law of conservation of matter. But I'm not going to say that the atoms can never be created. We have created atoms in the labs, and Here, berkelium, livermorium, those technetium, these names came from the labs, so these have been, mendelevium also is, I think, made here in California, or californium, you see. So these elements, atoms have been synthesized, So now we talked about already the charges. Now here, how were these charges discovered? How do we know that there is a positive charge, there is a negative charge? How do we know that? So we also know that one thing, that anytime there is a positive charge, there's going to be repulsion. Anytime the negative charges come close together, a repulsion. But anytime there is a positive and a negative charge, there is attraction. Okay, so look at this J.J. Thomson. J.J. Thomson, he was he studied the behavior of the atoms in a closed tube. So different gases he put them in glass tubes, and he passed electrical current, and he wanted to see what would happen or in the charged tubes, and do they get deflected, do they get attracted to the positive side, negative side of the electrodes, or even the magnetic field, those things. So that's called the cathode ray experiment. So here, the cathode rays contain negatively charged particles, and these particles, now called electrons, have a much smaller mass than the atom. So Thomson, he is credited of finding the electrons. And he said that these electrons are present in the atom. So in his view, he said that, okay, they are present just like a plum pudding. So the base or something inside the atom is positively charged, and outside, like the plum are there, like a what is it called, a muffin, with the blueberry muffins, like that, but more round. But anyway, so there's like just those blueberries are all over. So same thing like that. Okay, but Rutherford said, okay, he did a gold foil experiment, and he said that positively charged particles are present, and where are they present exactly? I mean, he wanted to study the structure of atom, is this correct or not? So what he did was, he took let's look at this. He took the gold foil, as you can see, the yellow colored foil in the middle, and outside is that purple colored circular, in the form of a C, that's a detector, okay? And so he took a lead chamber, and in that he put a source of particles. Now, that time, actually, it's the alpha particles, basically, and that's coming from a radioactive material. But you will study this more when you study the nuclear chemistry. But here, he passed this beam of light through a small hole. So he knew, very straight line, these particles were moving. Okay. So what happened is that several of the particles got deflected, were passed through the gold foil. Gold foil is very, very thin gold foil. So several of these particles passed through, but there were some that got deflected. Means that these are positively charged particles. There has to be something positively charged inside inside this gold foil, which repelled the positively charged particles. That is why they got deflected at different angles. Okay, so majority of the particles went straight, but the moment they hit the positively charged nucleus, boom, they were, forced to, like the repulsion, they moved in other different directions. So he found that, yeah, majority of the atom is empty space, but there are positively charged centers. So that gave the structure of the atom. So the structure of atom is, as we discussed, the nucleus is located in the center of the atom, contains protons and the neutrons, and represents the big mass of the atom. And the electrons, they occupy large empty spaces around the nucleus. And so the structure of atom basically looks like this, the one over here. So if you take, for example, this is a lithium metal, it's under the soil, under the oil, and you take a little bit of it out. So it is made up of only one type of particles. These are all one type, lithium, soft, metal made up of only one type of particle. So now we are just focusing only on one particle. These are several particles, but now just focus on one particle. So here we see that in the middle part is the nucleus. This nucleus contains the protons and the neutrons, and outside these electrons are moving. Then they said, okay, they are moving in the energy levels. So we covered all the mass, and then we discussed all the charge is the mass and the number of electrons. So we discussed that. Now, before that, I actually want to see if I missed something here. I might have. So we discussed that already. Group 1A, alkaline earth metals, halogens, solutions, characteristics. Yeah, this is what I missed. Okay, here, let's cover this. Characteristics of the metals, non-metals, and the metalloids in the periodic table. So we talked about it that, yeah, metals are in one side, non-metals are on the other side, but what are the characteristics? So here are the characteristics, that the metals are shiny. All the metals are shiny. They are ductile, means that you can make them into wires, okay? They can be hammered into thin sheets. That means they are malleable. Aluminum foil, silver foil, gold foil, like you saw the gold foil experiment. And iron, iron, copper, all these can be made into thin sheets, okay? And they're also good conductors of heat and electricity. Good conductors of heat and electricity. So if you pass electrical current through them, look at copper wires, they conduct electricity, we get the bulbs and light it up, okay? And they can be made into, jewelry and all those things. Density generally is very high, okay? And the melting points and boiling points are also very high of all the metals. So in this case, this is an example of silver, but pretty much all the metals have the same characteristics. Now comes the metalloids. Now, what's the deal with the metalloid? They could be shiny, could be, and they are brittle though. The thing is, if you hit them or you stretch them, here, when you stretch a metal, it becomes a wire. That means it has got a very strong tensile strength, but metalloids are brittle. You stretch them and they will break. On the other hand, you take a hammer and you start beating the metals, then they convert into thin sheets. They don't break easily, but they're going to flatten. Okay, they flatten and become sheets. But the non-metalloids, they shatter. When you hammer them, they will just shatter, break into thin pieces. Here we have their metals are the good conductors of heat and electricity. Metalloids are the poor conductors of heat and electricity. Or they're semiconductors. That is why silicon is used as a semiconductor in the semiconductor in the computers, right? Chips. Okay, so poor conductors of heat and electricity. Next comes the like they are used to harden lead, color glass, and plastic. So they are like kind of little bit, they have a very different type of uses, like we talked about semiconductors. But anyways, the density again, they are heavier. They are heavy, and melting points are also very high. So that's another thing. But the non-metals, on the other hand, they are dull. They are, they exist as gases, even if they are solid, like for example, sulfur or phosphorus. If you hammer it, it will not, it will shatter. It's brittle. It will break up into small parts. It is a poor conductor of heat and electricity. It's not going to conduct electricity, heat, those things. And again, density is low. Melting points, boiling points are also lower than metalloids. Okay, so this is something that I had to cover that. Okay, next, now we are looking at the atoms and the energies. Okay, now, how was the energy? How did we come to know? We covered this earlier here, that the atom is made up of electrons, protons, neutrons, which is fine. These are the small particles present in the atom. And the neutrons and the protons are in the middle, and they form the main bulk of the atom. But the electrons are present outside the nucleus, and they are present in the energy levels. Now, how did we come to know of the energy levels? How did we come to know of the energy levels? So these energy levels were discovered through light. Okay, now we are looking at energy levels. So these energy levels were discovered through light. So let's look at this. Okay, so we know that light is made up of different colors, right? 7 colors: violet, indigo, blue, green, yellow, orange, red, right? So that's one piece. And we also know that when light passes through, generally all these 7 colors combine and they make up the white light. But the light, when it passes through the prism, then it breaks, so you saw the structure, the rainbow. Besides that, we had known X-rays, we had known, radio waves. So we had also discovered the, properties of light. And we also understood, when we talk about the waves, wave mechanics, we understood that there are waves and then the waves and their frequency. Wavelength, there is a wavelength and the frequency. Wavelength is the distance between the 2 troughs or the 2 crests. Okay, and what are these? We'll show you in a minute. And the frequency is how many waves are passing per second. Okay, so that's one thing. So we know that the higher the radiation, the higher the radiation is, the shorter the wavelength is. Wavelength is the length of the wave. So the longer the wavelength, the lower the energy is. The shorter the wavelength is, higher the energy is. Means more waves are passing. So frequency is higher. So we understood the relationship between the wavelength and the frequency. Okay, so you guys don't need to, if you're not getting it, then don't worry about it. It's all coming from physics. So we understand that every element, when you take an element, you heat it. From solid, it goes to liquid. From liquid to it becomes gas. Now, in that gaseous state, when you pass it through a prism, it breaks up and you pass the electrical current through it. So the particles actually begin to jump. The electrons, they begin to jump. They jump from a lower energy to a higher energy level, higher energy to a lower energy level. And when they jump, they emit light. And we know that light is associated with wavelength, is associated with frequency. The color of the light, the red color has a certain frequency, the blue color, the green color, the yellow color, the orange color, and the red color. Now, how do we know that? Because we had discovered that there were several other radiations present. So this is the electromagnetic spectrum. Okay, this shows the arrangement of the wavelengths of the electromagnetic radiations with a visible range from 700 to 400 nanometers. Okay, so we had discovered, these are the X-rays, okay, and then we had discovered the gamma radiations from the radioactive sources. So gamma radiations are very, very dangerous. They are short frequency. You see how this wave is coming so close, so fast. These zigzag. These are the waves. So too many waves coming, too much energy coming. That is why gamma radiations are dangerous, very lethal. Then X-rays are fine. They penetrate to the skin, but they can be blocked by the bones. And so X-rays still are high frequency. High frequency is too many waves coming. You see the white color, up and down. That's the waves, too many waves. But then comes the ultraviolet. Ultraviolet are the ones that can kill bacteria, those things. So we see that the X-rays can be blocked by the bones, but the ultraviolet can be blocked by glasses. You can wear the UV light glasses, and then you can pass the you can pass through the ultraviolet without damaging your eyes, but they can kill bacteria, UV light. Okay, then after between the UV light and the infrared is our light, our spectrum, the visible spectrum, the one that we see. We don't see generally, we don't see the UV radiation, we don't see X-rays, we don't see gamma rays, but we don't see infrared radiations. We just know that's red color and the violet color, but our spectrum is this, the violet, indigo, blue, green, yellow, orange, red. This is our white light. So it exists. So if you look at this now, see these are the waves. So the distance that is in between the two troughs. What are troughs? This top part is a trough. What is this trough? This top part is a trough. What is a crest? This bottom part, you see the bottom part is the crest. Okay, and then the other one, the bottom part is the crest. So the distance between the two crests or the two troughs is the wavelength. So anyways, after the infrared radiation, we knew, the range. This is the frequency and the wavelength. This has been calculated. So we were able to calculate the frequency and the wavelength of microwaves and the radio waves, and all we knew was, if you know what is a frequency, if you know what is a wavelength, then you can identify the color. That color is associated with the frequency and the wavelength. And that color tells you, how much is the energy present inside that. So we know that for sure that this is low energy, but as you move, high energy. So even here, violet is towards the higher energy, the red is towards the lower energy side, and everything else is in between. So that is the electromagnetic spectrum. We already knew that. So what happens is that when we heated the electrons, when we heated our elements, pure, absolutely in its purest state, the purest state in which the elements can exist is the gaseous state, neutral gaseous state. Okay, anyways, so these electrons, they emitted radiations or colors of light, and that color of light, which is associated with the frequency and wavelength, gave out how much of the energy was there. So this is how the energy levels were discovered. So we have these energy levels. This is the energy level. Look at that, energy level 1, energy level 2, energy level 3, energy level 4. These energy levels are made up of sub-levels. So in a broader term, energy levels are called the shells, and the subshells are the parts of that big shell. So energy level 1 made up of 1 subshell, shell number 2 made up of 2 subshell, shell number 3 made up of 3 subshell, shell number 4 made up of 4 subshells. So that's one piece. Next is, if you look at it, what are they? The S, B, D, and F. These are the other types of subshells. That's a name, So 1S, 2S, 2P, 3S, 3P, 3D, 4S, 4P, 4D, and 4F. Those are the names of the actual subshells. Okay. Now, when we talk about the subshells, every subshell is made up of orbitals, and these orbitals are a place, are that region in space where the probability of finding the electron is the maximum. So these orbitals have shapes. So here's the thing, the S orbitals are round in shape. You see the blue color right here? That means in 3 dimensions, where is that electron? What is the probability of finding the electron? Where is that? What's that space where the electron is found? So we are now looking at a 3D model, not a 2D model. What you see here is a 2D model. This model is a 2D, 2-dimensional model. Where did it go? Here. So this is a 2D in 2 dimension. And remember, this was very specific. They exist as wave. They exist as particles. So if they are existing as wave and particle, and the electrons are rotating, and the electrons are spinning, how do we locate them where exactly they are? So this is how we give some meaning to that madness, that the probability of finding the electron is in this region of the space outside the nucleus in this energy level. So s orbitals, or orbital is the room in which the electrons are found. So the name of the room is S, so it's round colored. On the other hand, if the name of the room is P, then this is like Px, Py, Pz. These are the three dimensions, X, Y, and Z. And we can see the electrons horizontally, we can see them vertically, we can see them diagonally, okay? So here, these lobes, you know, they represent that region in space where the electron can be found. Next is the d orbitals. The bigger the energy level is, the more space they have. The more space means now we have more of these lobes, in other words. So you see, this is, so we are looking at the length, we are looking at the base, the horizontally, we're looking at diagonally, and everything else that falls in between. Okay, so that is the thing. Next thing is, we already talked about that they are spinning. So the electrons inside the orbitals are spinning, one going clockwise and the other going anti-clockwise. Okay, let's just discuss the other stuff. I have to that part. Now we will cover, I'm going to stop here and we will start, because it's a long video otherwise. So I'm going to stop here and we will start the electronic configuration and energy levels, you know, in my next video. Okay, thank you for watching. Bye.